But when we talk about rate constant, we're talking about a constant that's related to the rate of reaction. And in your section in your textbook when it talks about concentration, on page 549, it brings up this whole idea of quantifying, or kind of putting a number to a rate. And the rate of reaction is tied to, how the reactants react and how the products are formed. And so we can actually determine some numbers that are associated with how the rate is, or how the reaction is proceeding. So if you look on page 550, it's sort of where it starts to talk about reaction rate and a rate constant and a rate equation. So that's what we're going to kind of take a look at here today. So if you look at the example, it's hydrogen and iodine reacting to form hydrogen iodide. And of course the balanced equation would be 1 to 1 to 2. So what this chemical equation is saying, if you remember from your previous science classes, is that 1 mole of hydrogen and 1 mole of iodine produces 2 moles of hydrogen iodide. If we doubled the concentration of iodine here, so if this reaction happened, and now if we doubled the concentration of iodine, do you remember how changing concentration affects reaction rate generally? What did we say that concentration usually does to reaction rate? It usually, generally, increases it, right? So we're going to find that in this process, we're going to actually take a closer look at some data here. I'm sorry that this didn't copy real well onto this document, but we're going to take a look at some actual, lab trials and how they change concentration, and we're going to look at how the rate, reaction rate is changed. We're going to come up with sort of a summary or an equation for the rate. So doubling the concentration of I2 while holding the concentration of hydrogen the same actually doubles the number of collisions. So that makes sense, right? If you double the number of I2 molecules, you're going to have more collisions, right? And this, therefore, doubles the rate of reaction for this equation. This is symbolized by the following rate equation. Now, if you take a look at this, what this right here is saying is that the rate is equal to some constant, or you could say it's proportional to the concentration of I2. So the rate is affected somehow. In this case, is the rate constant. Now, we don't know what the rate constant is, but what we know is that the rate is affected by the concentration of I2. That makes sense. Now, if we look closer at a different reaction here, and again, I apologize for the fuzziness of this chart there. I hope you can kind of make it out. But it says, using the experimental data in the chart below, determine or establish the rate law and the numerical constant for K. So the rate law is basically the same as the rate equation. You'll hear me say rate equation as well. So rate law, rate equation. Now let's take a look at what's happening here. So the reaction is this. 2 moles of hydrogen gas reacts with 2 moles of nitrous oxide, producing nitrogen gas, 2 moles of water. And this is all happening at 10 degrees Celsius. Now, the temperature is important, as we know. A change in temperature changes the reaction rate, right? So the temperature in these trials must remain constant. That's the only thing. It doesn't matter what the temperature is, really. But what matters is that when we're determining, when we're quantifying the rate or stating the rate law, the temperature needs to be consistent throughout all the trials. So don't worry too much about the temperature. It doesn't actually come into play as far as, it doesn't enter into the equation, other than all the trials that we're doing here need to be at the same temperature. Okay? And any rate law or rate constant that we determine always is a rate constant at this temperature, because the rate will change at a different temperature. So don't worry about the temperature right now, is all I'm saying. All right, so test 1 or trial 1. What they have here is they have, in this chart, they have concentrations of hydrogen and nitrous oxide here, NO. And those are the reactants, right? So we're just focusing on the reactants and the concentrations of what we start with. Please notice that in most charts you'll see the square brackets here. Now, hopefully you remember what square brackets mean. I guess I've kind of been assuming that, but what do the square brackets around H2 mean? What does that mean? Yes, thank you. The square brackets refer to concentration. So if you are confused by that or unaware of that, then the square brackets is concentration, okay? And of course, this is concentration of hydrogen, molecular hydrogen. So you'll also see in here that you'll see, and I'll just highlight this, it says concentration H2 times 10 to the negative 1. So this 2.0 is actually 2.00 times 10 to the negative 1. And what is that? Well, that would be in moles per liter. So that's the other thing. The units for concentration are moles per liter. And again, this is physical science 20 stuff, so you've learned this once. I don't know if you remember it or not, but moles per liter is how we express concentration. And that's literally the number of moles in 1 liter. Okay? That's what capital M stands for. So, as we go back to the chart here, let's see. Hydrogen concentration is 2 times 10 to the 1, or 0.2. Nitrogen, NO's concentration is 1 times 10 to the negative 2. And we're given a rate of reaction. So they've allowed this concentration and this concentration to react, and they've noticed that we have a certain rate of reaction. In trial 2, what's happened in trial 2? This has changed to 4, right? So the hydrogen concentration has doubled. This has stayed the same. And it's important when we're doing trials or when we're looking at data, just make sure you look at 2 trials where one of the concentrations has changed, not all of them. Because if we change more than one thing, we can't really attribute the overall change to either one. We don't know. So it's like we got to hold one constant and then just change one thing at a time, right? Just like in anything in life, if you're trying to determine what the problem is, just change one thing at a time and see if that affects things, right? Right? If it's Christmas, it's coming up to Christmas time here. So if we're talking about Christmas lights on a Christmas tree, how many of you have those lights where if one bulb goes out, the whole thing goes out? Anybody have those, or you've seen those? Anyways, there's some lights that are, quite a bit more expensive that doesn't do that. But a lot of the cheap lights, if one bulb goes, the whole string goes. And so this would be an example of, you don't pull them all out at once and change them all. You pull one out at a time and change that one and see if the lights go back on, right? So you're just manipulating one variable at a time. So that's what we want to keep in mind here. We're going to double this, and I'm going to write here times 2. Okay, this is how I'm going to model this for you, kind of what I do on these charts, times 2. And then what happens to the rate here? It goes from 2.5 molar per second, or times 10 to the negative 5 molar per second, but it goes from 2.5 to 5. So that is doubling as well, right? And what this tells us is that the rate, okay, the rate is directly proportional to, and we're going to say that there's some kind of constant. It's directly proportional to the change in hydrogen concentration. So we've got that so far. Now, there will be some cases where a change in some of the reactants won't change the rate. It happens because they might be a multi-step reaction, or different things might be happening. But in this case, the rate is directly affected by the hydrogen ion concentration. Can you see that from the chart so far? Doubling the hydrogen concentration doubles the rate. You good? Yeah? Okay. So let's take it now, just for clarity here, I'm going to erase this. You don't have to on yours, but now we're going to let's look at something else. Well, actually, we could check this. Let's check another 2 trials, trial 1 and trial 3. This is times 3, from 2 to 6. So what's happening to the rate? Now we're assuming that if this is a direct relationship here, that this should triple as well, and does it? 2.5 times 3 is 7.5, yes. Okay, so we've confirmed that the rate is directly proportional to the change in concentration of hydrogen. All right, let's see what happens when we change NO. What happens? Well, let's see. Okay. Now you have to pick 2 trials, and if you can look at this for a second, Pick two trials where the hydrogen ion stays the same, but the NO concentration changes. Which two trials might we want to consider? Okay, 5 and 6 was mentioned. Let's see. This is staying the same, and this is changing. Good. Yeah, that we could do that one too. I'm going to suggest something. The reason why I would steer away from comparing these two trials is because 2 to 3, that's not like a double or a triple or something. That's times 1.5. So let's try and find two trials where we're looking at a straight, like a double or a triple or a quadruple times. Okay, 5 to 7. What's happening between 5 and 7? So 5 and 7, this is not changing. That's good. And this is doubling. Okay, good idea. Let's do that one. 5 to 7. So this is staying the same, and we are doubling. You see that? That's 2, and this is 4. We're doubling the concentration here of NO. So now what we want to see is what's happening to the rate. And it's going from 10 to 40, the rate. So what's that? That's times 4. Yep. So actually the change in NO affects the rate more than the change in hydrogen, right? So in our rate law, we want to definitely put NO in here, okay? And what you do is you put it like as a multiplication, so it's K times H2 concentration times NO concentration. But this whole times 2 and times 4 thing, we have to account for that. We have to say somehow in this rate law that the concentration of NO affects the rate at a different rate, or more than the concentration of H2 does. And this is what we do. Instead of saying, you know what, this is doubling, but this is quadrupling, this is what we're going to do. We don't actually put coefficients in. Like, we wouldn't do anything like this. We wouldn't put coefficients in. Instead, what we would do is we have to work with exponents only. All right, so think about this for a minute. What exponent would I put here? Because I've actually put an exponent here. What exponent have I put here without writing one? 1, okay? So, just looking back, hydrogen concentration is directly affecting the rate. So as the hydrogen concentration changes to the power of 1, that's how the rate changes. Doubles, doubles. Triples, triples, right? But NO, let's think about a power. So how can I write 4 as a power? And here's the hint. If this is doubling, can I write 4 as a power of base 2? Yeah. Okay, 4 is the same as 2 squared. Okay? So here's the tricky part. When we're doing our rate laws, we have to describe how the concentration change affects the rate using an exponent. And so what you do here, this is changing by 2 to the power of 1. This is changing by 2 to the power of 2. So it's a squared relationship. So that's what we do. We put a 2 here. Okay? So that's how we build this rate law. So if we summarize what's going on here, it's a bit tricky to summarize, but let's attempt to summarize what's going on here, how we build the rate law. Okay? So, let it go. To build the rate law or rate equation, we examine lab trials and concentrations of reactants and rates. So just as we complete the notes here to describe what we've just done, to build the rate law or the rate equation, we examine lab trials and the concentrations of reactants and the rates of equation. So up here in this chart, we've got concentrations and we've got rates. what we want to do is we want to notice if a change in concentration of a reactant affects the overall rate. And that's what we did with hydrogen and with nitrous oxide here. We said, yes, hydrogen affects the rate. Double hydrogen doubles the rate. And yes, nitrous oxide, if we change that concentration, that affects the overall rate as well. Nitrous oxide, if we double NO concentration, then we quadruple the rate. We then determine to what degree the change in concentration affects the reaction rate. And that's why, times 2 and times 2 squared is sort of how we're trying to connect the changes. And so we write this in the rate equation as an exponent. And so doubling and quadrupling turns into a change in concentration squared, because 4 is 2 squared. So we're always looking for exponents to put in our rate law, not scalars or not multipliers. Exponents always. Okay. If the reactant doesn't affect the rate, it is not included in the rate equation. And so the rate equation does not have to include all of the reactants, just the ones that affect the rate. And then finally, the rate constant K can be determined using data from one or more trials to complete the equation, which is what we're going to do right now. So if you've had a chance to get these notes down to absorb some of this information here, we're going to go ahead and do B, calculate the numerical value for K, the rate constant, which is of course attached to this temperature of 10 degrees. And how we do that, and we've already had a suggestion on how to do that, and that's totally right, totally correct. We want to include the rate, the concentrations of the reactants involved in the rate law, and to solve for K. And so we pick any trial. It doesn't really matter which trial. You might want, it doesn't matter. I mean, you might want to pick trials that have some smaller numbers or whatever. It doesn't really matter. But this is what we're going to do. The rate, let's just do trial 1. And so what do we put in here? The rate is 2.5 times 10 to the negative 5. So let's do this here. So rate constant. 2.50 times 10 to the negative 5 equals some value K, and that's what we're determining, times, now let's use the concentrations of hydrogen, which is 2 times 10 to the negative 1, or 0.200. And that's to the power of 1, right? You don't have to write that, but it's to the power of 1. And then that is also comes from the concentration of NO, which is 1 times 10 to the negative 1, or 0.100. 3 sig figs mentioned there. That's going to help us determine how many sig figs there. The answer should have 2, right? But this is squared. Okay. So we simply plug in our values, and we solve for K now. So, now we divide both sides by 0.2 times 0.1 squared to get rid of that, and this will be our answer for K right here. Okay, so for a K value here, you evaluate this 0.0125. 3 sig figs right there, 0.0125. Okay, so confirm that on your calculator as well. But the entire rate equation now is this. The rate of this reaction at this temperature under these conditions, the rate is exactly affected this way. 0.0125 times the concentration of H2, or wait, was this H2? Yeah, and times the concentration of NO squared. So there is your rate equation. Here's your value for K. All right, so that's the instruction part there on rate law, and we'll do some more examples. But yeah, you might want to look over this again. But that's how the rate constant, the rate law, is determined.